A very good day to all. Today we are going to have the revision session for Chapter 3 on the simulation of reactive processes. The revision will be done based on two exercises. Exercise 3.6, which has been given to you earlier, and another exercise is exercise 3.8. So let's shift to the PowerPoint. So in exercise 3.6, we are having a case of ethylene oxide to be hydrated to become ethylene glycol. So the reactor is operated at 55 degrees C isothermally. 1 pound mole per feet cube of solution for ethylene oxide in water is fed to a CSTR together with an equal volume of water. So the sulfuric acid is used as catalyst, and the reaction is first order in the concentration of ethylene oxide. The specific reaction rate given is 0.311 per minute at 55 degrees C. So the question to you is, if 80% conversion is to be achieved, what is the required reactor volume? So the conversion over here is referring to the conversion of the limiting reactant, which is your ethylene oxide. So let's analyze the problem before we solve the problem. So we have the recommended property method here is unique because of the low pressure process, and the process also involve polar liquid phase reaction. The reactor model, for sure we are going to use RCSTR because the kinetic information is given, and we are asked to determine the volume required to achieve 80% conversion. To start with, we can actually put the reactor volume as any volume. In this case, I recommended 25 feet cube. As stated in the question, there are 2 feet. 1 feet is ethylene oxide solution, meaning is ethylene oxide in water. The molar flow rate is 405 pounds mole per hour, and the concentration of ethylene oxide in this solution is 1 pound mole per feet cube. To calculate the volumetric flow rate, you have to use the molar flow rate divided by the concentration of ethylene oxide, and the total volume for the ethylene oxide solution is 405 feet cube per hour. Similar to the feed 2, which is a pure water, the volume also should be 405 feet cube per hour. So let's solve a problem. As usual, we have to generate or create a new blank simulation. Then we have to include the list of components, select the property method, and generate the properties for all the components before we shift to the simulation environment. The first step in the simulation environment is to construct the flow sheet, which consists of a CSTR, 2 feeds, and also 1 product. You can name the CSTR accordingly using the appropriate convention. In this case, I have actually named it as R101. So once you have done constructing the flow sheet, then we include the feed specification. As mentioned earlier, we are having 2 feed. The first feed, the one on your left, is actually the ethylene oxide solution. This is a little bit different with the case that we have solved earlier, because normally we'll specify the molar flow rate or the mass flow rate, and also the mass fraction or the molar fraction. But in this case, because we are having ethylene oxide solution, we specified the volumetric flow rate 405 feet cube per hour, and we also specified the solvent as water. And on your right, when you specify the composition, you have to specify the concentration of ethylene oxide as 1, and please select the unit accordingly. So we have done for the ethylene oxide solution. we have to include the feed specification for the pure water. The volumetric flow rate is the same, 405 feet cube per hour, and the mass fraction for this stream is 100% water, so we put 1 as the mass fraction on the composition section. Done for feed specification, we move to reactor specification. Pressure and temperature are 1 atm and 55 degrees C respectively, and the reaction happen in liquid phase. As mentioned in the analysis section, we put the initial volume as 25 feet cube, so just choose reactor volume at the specification type, then we put 25 feet cube. Next is to include the reaction details. We are having only one reaction, which is hydration of ethylene oxide to produce ethylene glycol. So just include the chemical equation accordingly. So this is a chemical equation. You have to include the chemical equation in the configuration section. Once you have done that, under kinetic section, you can choose this reaction, hydration of ethylene oxide, and include the details accordingly. So the unit given here is per second basis. We have chosen the 1 per second basis. So we have to convert, or we have to change the unit for K value, the rate constant just now, to per second basis. So the one given is per minute basis. So once you have changed it to per second basis, it is actually 0.005183. Just include accordingly. And don't forget to include the driving force, which is the order of the reaction. The reaction is first order in ethylene oxide. Just put 1 here to indicate that it is first order in ethylene oxide. So next is to include the design spec. Of course, before you have the design spec, or before you perform the design spec, you can actually run the simulation and get the result for the volume of reactor of 25 feet cube. But our target, of course, is to determine the volume required for the 80% conversion, and 25 feet cube may not be sufficient. Now we have to do design spec to identify the volume required. So let's define the design spec under the define section. This is of course, as you know, design spec is under flow sheeting option. Just go to flow sheeting option and create a new design spec, DS1, and you have to include the define parameter. So we define the inlet flow rate for ethylene oxide and the outlet flow rate of ethylene oxide. Okay, we define these two, and we have to shift it to specification to include our targeted conversion. So as you know, conversion is defined as the inlet flow rate of ethylene oxide minus the outlet flow rate of ethylene oxide divided by the inlet flow rate of the ethylene oxide. So we include the equation accordingly, and we include the target as 0.8, and the tolerance is 0.001. You can increase the tolerance or you can reduce the tolerance to give you the accurate result. So in this case, 0.0001 is good enough to give you the accurate result. So once you have done this, then we shift to varying parameter section. So here we have to vary the volume of the reactor from 1 to 300 feet cube, say. So you can choose the unit as well. So here I have chosen feet cube, and I would like to vary from 1 to 300, and the step size is 1. That means the interval would be 1 feet cube. So once this is done, then just click next if you don't know which step to go next, and you are asked to run the simulation. Just run the simulation and you can check the result under the results tab. This is the results tab under the block section, block R101, and the volume required is 32.6 feet cube for achieving 80% conversion. You can also check the result under the design spec, the result section. There's a result section. Initially, the volume is 25 feet cube, but after the design spec, the volume required to achieve 80% conversion is 32.6 feet cube. So I think with this we have answered the exercise 3.6. Thank you very much. I will meet you again for exercise 3.8.